yesterday. So the question was, what was the derivation of the Polyakov action? Okay. And okay, so first we are going to derive the following equation. So we're going to find that the trace of the stress tensor is equal to the curvature on the world sheet times the central charge times a numerical coefficient that I'm not going to compute, but can be computed by the method I'm going to explain. Okay, so the central charge was defined by the CC components of the stress tensor. Well, I was asked to write bigger, and I'm already realizing that I have forgotten about that. So if I write small, please remind me to write bigger. What we're going to do is we're going to take a C-bar derivative of this, and so the C-bar derivative of this, so exercise is equal to the C derivative cube of C over C times delta function of C minus C prime. Okay, this is just the two-dimensional delta function. I mean, the equation you really need to prove is that this is the two-dimensional delta function. Okay? Well, I mean, we can even prove it here. So, right, and this is the Laplacian. This is the well, you know this formula. Okay, so we start with this, and then we say, okay, we use the conservation of the stress tensor to conclude that this C of T C bar C, C, T, C, C, C prime, this is equal to, well, the same thing, and so we write this as dC of d squared C of delta of C minus C prime, okay? Now we integrate with respect to C, and we get this equation. Notice, normally we say in conformal field theory this operator is 0, but, well, here it's 0, so away from C equal to C prime is 0, and all the correlation functions have only this contact term. So you need this contact term in order for the stress tensor to be conserved. Anyhow, so now what we concluded was that the trace, this is the same as the trace of the stress tensor, so this is the same as T mu mu, times this is equal to this correlation function. And now we think about this as the trace of the stress tensor on a space which is flat space plus a small little correction. So this is flat space plus a small little correction, which is a change in the metric of the component in the metric GCC. And we can compute this by, so the leading term in the small fluctuation of the metric comes from this two-point function. So the leading change in the action is just to bring down this stress tensor, and we'll get that. Now, that is to say, we consider here delta GCC, we integrate dC prime, and so we integrate here dC prime, and what we get is dC squared GCC, and this is just the curvature evaluated to first order, okay? So what we found is that this is equal to C times the curvature, and so that was the first point. And now a change in the Weil factor of the metric, well, I guess I should say that, so this is the curvature to first order, and then by coordinate reparametrization invariance, the only thing that this could be is just the curvature itself, okay? So when we consider a nonlinear curved space, we consider to all orders, just reparametrization invariant fixes it to be the curvature, if it was the curvature to first order. Now also what appears here is determined by dimensional analysis, so this is an operator of dimension 2, and so this should be some object of dimension 2 built out of the background metric. Okay, so this is a formula valid for any conformal field theory, and Okay, so the leading change in the action, so if we change a little bit the Weil factor in the metric, that's the same as the integral square root of g, t mu mu delta phi, and t mu mu delta phi, so this expectation value is equal to the integral square root of g r times delta phi. So this is the change in the action when we go from the metric g to the metric g plus delta phi times g. Okay? And then the full Polyakov action is obtained by sort of integrating this equation with respect to phi. Okay? This you can do. You can think about this as an exercise, or you can show that if you start with the Polyakov action and you make a small change in phi, what you get is roughly like in other words, if you set this to 0, that would be the equation of motion for the Polyakov action, and you can check that the equation of motion for the Polyakov action is just grad square phi plus r, and this is and basically this is the same as computing the curvature of the original metric g. Okay. Okay, so now, so that finishing this derivation is an exercise. Okay, that finishes the answer in that question. Now we'll go back to the main topic of the lectures. And so last time we discussed this field theory, which was n equal to 4 UN super Yang-Mills theory in 3+1 dimensions, and we saw a bunch of properties of this theory. So one was that it's conformal. The other one was that it has an SO6 symmetry. It had an S-duality symmetry. It also had a bunch of supersymmetries. So the number of supersymmetries is 16. And in any theory that is so naively, you would say that this theory has 16 supercharges. So it has 4 supersymmetries. In 4 dimensions, each supersymmetry has 4 components. So that's 16 supercharges. However, conformal invariance implies that there are 16 extra other supercharges. And so in total, we have 32 supercharges. Okay, and all the symmetries combine into a supergroup, sometimes denoted by PSU 2,2/4, I think. Yeah. Okay, so denoted like this is just a name for this group, but it's a group that results from combining all the symmetries. Okay, now, so this is the field theory, and this will be, so we said that it had to be related to some 5-dimensional background, which was of the 5-dimensional anti-de Sitter space. Now this theory is very supersymmetric. It has the same supersymmetries as string theory in 10 dimensions. So you might think, oh, maybe it has something to do with 10-dimensional string theory. And if we added one more dimension beyond the number of dimensions of string theory, beyond the number of dimensions where the field theory was defined, it wouldn't surprise you to add 5 more dimensions. Just to. And so here we add 5 more dimensions. And so now we have a 10-dimensional background. But this SO6 symmetry suggests that a good choice for these 5 extra dimensions of a space that is SO6 symmetric is S5. So we have this sort of candidate background, and indeed this background is a solution of type 2B supergravity, with a background 5-form flux. So you can write the action of type 2B supergravity. You can truncate it to just the metric plus. This action is schematic because the 5-form field strength has to be supplemented with the self-duality condition, which doesn't follow from this action. But basically, you take this action, and then you say that you have some magnetic flux of F5 over the S5, okay? And this magnetic flux will be quantized, so because there are different D3 branes, and they come with a certain unit of charge, so and that will quantize the 5-form. This magnetic flux is 5-form, and in those units, this is some integer n, and so the 5-form flux is quantized roughly in this way, with some numerical coefficients here that I'm not keeping track of. Okay, so you try to find the solution of this form for this action with this flux, and that then you find that indeed there is an AdS 5 cross 5 solution with a particular radius. So this, once you plug this into the equations, you'll find the relation between the radius of S5 and the radius of AdS and the overall value of the radius. And what you find is that the radius is equal to, well, if you put in, well, let me not put in numerical factors. This is like G string n to the power 1/4 times Ls, or this can also be written as 1n to the 1/4 times L Planck. Okay. So in Planck, in 10-dimensional Planck units, the radius goes like n to the 1/4. Okay. Now I'll just mention maybe a little more on how what sort of stabilizes this radius, this particular value. So this is a little calculation that, well, it's not, it's a side comment, but it's a useful way to think about it. So you can think of this. First, we think of simplifying 10-dimensional supergravity onto an S5, okay, leaving this manifold arbitrary, and that will give us an effective on an S5 with radius little r. So r will be the radius of S5. So we'll have a space which is something which is 5-dimensional plus this S5. And so the action will have a term like r to the 5th square root of the 5-dimensional metric times the 5-dimensional curvature. And then it will have a term with that will come from the energy of this 5-form field strength. So this 5-form field strength has a strength of, let's say, n units, and so we can figure out the r dependence of this term. So this r comes from the determinant of the internal 5 dimensions, and then here, when we compute this energy, we'll have f mu 1, mu 5, f mu prime 1, mu 5 prime, and then we have g mu 1, mu 1 prime, etc. 5 times. Okay. So this is so if we, for example, this mu are the angles on a phi sphere. So then here this is just an integral over those angles. So f5 is independent of the radius of the sphere in those units, and so in other words, this whole combination will go like r to the minus 10. Okay, so we get 1 inverse power of r squared per inverse metric. Okay, so times this r5, this whole term goes like r to the minus 5. Okay, so this is a positive contribution to the potential. Okay, so it's the Lagrangian has something minus a potential, so this is positive contribution to the potential. And then we have a negative contribution that comes from the curvature of the S5. So this will be, the term we already wrote was the curvature of the 5-dimensional space, and then we will have the curvature of the S5. And that term goes like Well, so we have the G5, and then we have the R to the 5. And curvature goes like the inverse. So it's something that has units of 1 over length squared. So in terms of the metric, we'll go like 1 over R squared. So we have the R to the 5 minus 2. So here we have the R cubed. Okay? And now we can now find. You would be tempted here to take a derivative with respect to R and set R equal to 0. But that would not give you the correct answer. So in general, it's not correct to plug answers into the gravity equations. However, what gives actually the correct answer is to now move into Einstein frame. So here we define a new metric so that we absorb this factor of R. So as an exercise, you can find the correct factor. So that you define a new metric G Einstein, which is R to some power here that you can find as an exercise times this 5-dimensional metric that is appearing here. And so then you can rewrite this as G Einstein R Einstein minus some potential B of R. And this potential B of R that potential will be some overall factor times what we already computed. So B of R will just be R to the minus, well, some factor here that is negative times n squared R to the minus 5 plus minus R cubed. Okay? So we can now plot this potential. Well, maybe I should say what this power is, because otherwise... okay? So this power is such that this number is more negative than the 3. So the potential at infinity goes to 0. So this is R. So this direction is the R direction. And this is R equal to infinity. This here is R equal to 0. And here we are plotting B of R. So the potential goes to 0, and that's the generic feature of Kaluza-Klein compactification. So you can check as an exercise that in any Kaluza-Klein compactification, the potential will go to 0 at infinity. The curvature, positive curvature in the internal manifold contributes negatively to the energy, because that's how curvature appears in the gravitational action. So this is R, so and the Lagrangian has a minus potential, so positive R is like a negative potential. Okay. And then the field strength contributes positively, so in the end you find some stable minimum, some stable anti-de Sitter minimum with negative value of the vacuum energy, so that gives you this anti-de Sitter compactification. Now, from these powers of R that we saw here and this power of n, you can see that if we balance these two powers, we'll get some equation which will be something like n squared times R to the minus 8 equal to some constant, okay? So this is saying that R goes like n to the 1/4, and that's precisely what we found before, okay? So I have just derived for you this particular dependence of n, of R with n. Okay. So that was a sort of side comment. Now we go back to this relationship. Now, before going back, I'd like to now explain one other argument for why these two theories are related. So why string theory on AdS 5 cross S5 should be the same as UN Young-Mills. And the argument, I'm going to just only sketch the argument. So the argument is the following. You consider a stack of n D3 branes in R10, so in 10-dimensional flat space. So we have flat space here far away, and we have this n D3 branes. And so as you probably saw, the theory living on the n D3 branes is some open string theory. And at low energies, this open string theory reduces just to the theory on the massless modes. So at low energies, so we have we have n equal to 4 Yang-Mills theory on the brane. On the other hand, we can, so that's from this D-brane point of view, and this is a point of view that is valid when the string coupling is extremely small, when Gn is very small. So there in that, from that point of view, in that case, this Yang-Mills theory will be weakly coupled, and the derivation of the theory will be absolutely correct. Now we view the same system, but from the sort of gravitational point of view, we have some 10-dimensional supergravity action, and here at infinity, these three branes create a 5-4 field strength because the three branes are charged under the 4 form, and so they generate some electric and magnetic fields. And these electric and magnetic fields back react on the metric, so the metric that originally was flat will not be flat when you start approaching the brane, and instead of that you'll have some sort of space that is flat far away, and as you approach the brane is some sort of curved space. Okay? So this will be a geometry which is sometimes called extremal black brane geometry. It's somewhat similar to an extremal black hole. So in fact, an extremal black hole in 4 dimensions has a near horizon. So here, going down here is like going close to the horizon of a black hole. And so if we have a geometry like this, and we consider low energy excitations, an excitation can have low energy because it has long wavelengths and is far away in this flat region, or an excitation, even if it has short proper wavelengths, if it is very close to the horizon, it will also have very low energy because there is the redshift factor vanishes at the horizon. So any finite energy excitation, proper energy excitation, when you put it at the horizon, will have 0 energy. So at low energies, from this gravitational point of view, so at low energies, we have this we concentrate on this near horizon region, and the geometry of this near horizon region is AdS5 cross S5. Yes. Yeah. Let me see. When am I going to explain? Okay. So what vanishes is the redshift factor. So this is a very important property. So let me explain it more in detail. That's the geometry near the horizon of this black hole. Okay. If you have an extremal black hole in 4 dimensions, and you look at the near horizon geometry, the geometry is AdS2 cross S2. Okay. So the S2 is the sphere that surrounds the black hole, and AdS2 is the combination of the time direction and the space direction. Okay. So this is the same thing, but in higher dimensions. Exactly the same thing. Okay. Okay, so let me now explain a little bit this the point I just said about the redshift factor. So we will have a metric which has a form, let's say in some coordinates, r squared dx squared plus let's say dr squared over r squared. But this is similar to the metric we wrote yesterday, except that I redefine r goes to 1 over c. So r equal to 0 is the horizon. Okay. And these coordinates include the time coordinate and some spatial coordinates. Now the factor that multiplies the time coordinate is normally called redshift. And this factor tells us the difference between proper energies and energies measured with respect to the time t. So the time t is the isometry that this space-time has, and it's really the energy measured at infinity. Okay? And that's the same as the energy that an observer here in Young-Mills theory measures. So the energies in Young-Mills correspond to energies measured with respect to the time t. Okay, each are field theory energies, and so that's roughly like d dt, and these are equal to r times proper energies. Okay, so these are like the derivative with respect to proper time. So this we can call the tau squared, and tau is proper time. Okay, so we find this relationship, and so we see that if we fix the proper energy of some excitation, so in this case, for example, we consider a fixed Kaluza-Klein mode on the S5, that the S5 has constant radius, so that's some constant energy in proper units, and we move closer and closer to the horizon, then the energy measured from the field theory point of view or from infinity goes to 0. Okay. So that's why when we take the low energy limit in this space, so ordinarily in gravity when we say the low energy limit, that means going to long distances, right? If you're in flat space, low energies means going to long distances. So any low energy excitation is some excitation with very long wavelength. In the presence of a black hole, there are two ways in which an excitation can have energy, low energy. Well, the first one, which is what we just said, a very long wavelength excitation far from the black hole, and the second is a short wavelength excitation, but very close to the horizon. Okay. So, okay. Are there any questions? Okay, I was sort of hesitant to make this argument because in this relationship there are no d-branes anywhere, and it's better to think about this relationship forgetting about the d-branes completely. Now, here what happens is that the d-branes in this geometry are no place, but in some sense the d-branes are this whole region of the geometry. If you want to ascribe some meaning to the d-branes, those d-branes are this whole region of the geometry. Okay, and the low energy limit, so the low energy limit of the field theory that lives on the brane is this region near the horizon. And if you consider it for all energies, then you include also this other region. Okay. But you should not think of the d-branes as either sitting at infinity or sitting at the horizon and so on. The whole geometry is dual to the field theory living on the branes. Okay. In a sense, if you send in a graviton from infinity, so you send in some particle, this particle comes in and goes down to the horizon. Okay, that's the picture here. The picture from the d-brane point of view is that a graviton comes in here, and then this graviton sort of excites some gluons on this Young-Mills theory, and the gluons separate. Okay. Roughly speaking, the point where the gluons separate, this interaction here, corresponds to the transition between this region far from the horizon to the region close to the horizon. Okay. So once this original graviton is around here, it's already been described as a bunch of gluons. Okay. Okay. So, yeah. You can choose other gauge groups. So now, so you can choose any gauge group, but only for SON or SPN you can take the Larsen limit. And it's conformal for all gauge groups. Now, if you had, let's say, SON, then well, SON basically corresponds to, instead of taking S5, you take S5 mod C2, where this C2 identifies opposite points on the sphere. And this C2 is an orientifold. Okay? So you reverse the points on the sphere, and at the same time you reverse the worldsheet orientation. As an exercise, something you could do is consider. Last time we saw this Larsen counting of for matrices that were in the fundamental, that were in the adjoint of UN, that were basically Hermitian matrices. You can do something similar for matrices in the adjoint of SON, and so those are antisymmetric matrices, and you can do the Larsen counting. And you will see that there will be one difference, will be that yesterday we had that gluons were disoriented lines. We had these lines that were oriented. Now we'll have this double line notation, but these lines are not oriented. And so when we start making Feynman diagrams, we can at any point twist one of these propagators. And as an exercise, you'll see that in this topological expansion we were talking about corresponds to adding non-orientable surfaces. So the expansion in terms of worldsheets that we had for Larsen theories before included only oriented two-dimensional surfaces. I didn't emphasize that, but you can check that as an exercise. And that was a consequence of these lines having these orientations. Once you drop that requirement, you have unoriented surfaces, and then depending on the sign that the non-orientable surfaces come in, they could come in with plus or minus sign, and depending on that, you have the SP or SON theory. Anyhow, so there are here various oriented fold quotients you can do, and some give you SON, some give you SPN. Okay? Yeah. Yeah. General enough. What do you mean by general enough? Yes. I see what you understand. So your question is whether a general black hole has a near horizon geometry which is AdS. Yeah. So that's a property of extremal black holes. So any extremal black hole will have a near horizon geometry which is AdS. Okay. Well, maybe I should qualify it a little bit. Any extremal black hole with a non-singular horizon. Okay. So the basic thing you need is that as you... Yes? What? The full metric, yeah, sure. Well, I didn't want to get too much into this. Well, maybe I'll the metric and then I'll... So I'm going to write down the metric for the black brane configuration, the general black brane configuration. Well, first let me write down the metric of the extremal one. So these are 3 dimensions, and then we have f to the 1/2 dr square plus r square d omega 5. Okay. So this is like 6 of the dimensions, the 6 transverse dimensions of the brane, and these are the directions along the brane. And this function f is 1 plus n over r to the 4th. Okay. So if you are far away, then you can drop this and you have flat space. If you are at r near 0, so when r, then this can be replaced by n over r to the 4th. And so this factor becomes something like r squared, and this factor becomes like 1 over r squared. This 1 over r squared cancels this r squared, so here you have the S5 with constant radius. And then we have the r over r squared times r squared times this thing, and that's the metric of AD. That's that metric I wrote over there. Okay, and that was the metric of ADS. Okay. Now, all other black branes, which are not these 3 branes, do not have near horizon geometries that are AdS. And the reason is that those other branes have other scalar fields, like the dilaton, for example, and the dilaton is behaving in a funny way as you go to the horizon. It's either going to infinity or going to plus infinity or minus infinity. And so for that reason, the geometry near the horizon will not, the curvature will blow up and funny things will happen like that. And so it's not a good geometry. And well, that has some field theory interpretation, and I guess maybe if I have time, we'll discuss that. Well, but now that I've sort of written out this metric, I'll jump ahead in the notes and describe some thermal aspects, which for which we'll need to write on this metric a little bit. And so we are in the near horizon geometry, so we neglect here the 1. And this metric has a near extremal generalization, in which here we put R0 to the 4th over R to the 4th, multiplying the time direction, and here 1 minus R0 to the 4th over R to the 4th. So this is not an extremal black brane, but a near extremal black brane. So if we have the 1 here, that's the near extremal black brane. We go to the near horizon geometry, we drop the 1, and we have this metric. So this is a black hole, and this is a black hole with non-zero temperature, and the temperature is basically proportional to R0. So as an exercise, you can calculate the temperature of this black hole, and in order to compute the temperature of a black hole, the way you do that is to go to Euclidean space. Well, here I forgot the minus, but in Lorentzian space you have a minus here. In Euclidean space you don't have the minus. And you look at the geometry of the time direction and R direction. And this geometry, in general, for a non-extremal black hole, will have the geometry roughly of a cigar or the geometry of a disk. And here, this is the point R equal to R0, where this factor vanishes. And if time has the right periodicity, then this will be a completely smooth point. If time does not have the right periodicity, then here you'll have a conical singularity. So the temperature of the black hole is determined by demanding that the periodicity in time, so that time is identified with time plus beta, and demanding that you do not have a singularity here, you get some value for beta. Okay? And in this case, you basically see from dimensional analysis that this is R0 over R0 squared and times R0 squared, and then you pull out the factor of R0. Then you find that the temperature, which is 1 over that period that we had over there, is proportional to R0. Okay, up to some pi's or whatever. So when we go to zero temperature, we recover the extremal solution. Now, something we can do is we can compute the entropy of this black hole by using the Bekenstein-Hawking formula, which says that the entropy of the black hole is equal to the area of the horizon. Now, of course, here we have an extended brane, so the area of the horizon will have a volume factor. So a factor, yeah. No. Well, you can do it as an exercise, but not. Yeah. Okay, so now we have the entropy. So the entropy has a volume factor. So I'm going to just divide by that volume factor. So this is the area per unit volume. And when I say volume, it's really the volume of the x coordinates. So in the same way that we said that the volume, that the time that appears here, this time appearing here, the time measured in the field theory, these x coordinates here are the x coordinates measured in the field theory units. So these are the Killing vectors of the spacetime. These are really the symmetries of the theory. So the translation generators in the field theory corresponds to shifts of these x coordinates. Okay, so we go ahead and we compute that. And this will give us some number, pi squared over 2, times n squared times t cubed. Okay? Okay, so that's the entropy. Now, I remind you that this Larsen counting that we did last time in field theory. So what do we expect in field theory? So in field theory, this so computing the entropy is really it's basically a computation related like to computing the free energy of the field theory. So what you're computing is you're computing the partition function of the field theory in a space-time that is S1 times S times R3. Okay. So you go to Euclidean space, this kind of Euclidean space, which is S1 times R3 of radius beta, and then you compute the partition function, and the log of this partition function is minus beta f, and f is the free energy, and from the free energy you can compute the entropy. Okay, now what result do we expect in the field theory? That the entropy in the field theory, well, now what dependence on n should it have in the top limit? So last time we discussed these large n counting arguments, and we found that n is roughly like, well, yeah, I guess I didn't completely emphasize this point, but we discussed that all correlation functions in the Yang-Mills theory went like n squared, and that's even true of the partition function itself. It goes like n squared. Okay, and well, I guess we saw that the diagrammatic expansion, the first term is a sphere, and that went like n squared. Okay, so the first term is the spherical diagram that goes like n squared, and so here we should have a factor of n squared. Okay, but this in general is multiplied by some function of g square n. So the Yang-Mills coupling times n. Okay, so that's the result we expect in general. Now, what kind of temperature dependence do you expect in the field theory? So this is a conformal field theory. So the theory itself has no scale. So entropy per unit volume has units of energy cubed, right? So the only thing that this can be is temperature cubed. Okay. Okay, so now we really need to compare these two quantities. And if you compute it at weak coupling, so at weak coupling you'll have pi squared over 2 times 4/3. So this is the result for the entropy at weak coupling in the field theory. And you see that they are different. Okay? Now, should we be worried about the fact that they are different? Okay. So in order to understand whether we should be worried or not, we really need to discuss in a little more detail when the gravity approximation is correct and when the weakly coupled field theory approximation is correct. Okay. So let's start with the field theory. So we have the field theory at weak coupling. So what does weak coupling really mean? So naively we would think that weak coupling means that chi squared Yang-Mills is much less than 1. Okay, that's naively what we would say. But really, the effective coupling constant of the Yang-Mills theory is not chi squared, but chi squared n, as we yesterday. So yesterday we saw that each time you add a propagator and so on, you get a factor of chi squared n. Okay. So this n comes from the n sort of gluons, from the n gluons that you can exchange between, let's say, two quarks. And so that's why you get this factor of n. So what for the weakly coupled calculation to be correct is that chi squared n should be very small. So this calculation here on the right-hand side is correct when chi squared n is small. Now, when is the gravity calculation okay? Now, we said we have AdS5 cross S5, and the radius of AdS5 cross S5 is Gn to the 1/4 times L string. So when is gravity a good approximation to string theory? So the one thing we need to ask is, when is gravity a good approximation to string theory? So if you have some space of some radius, right, this is some piece of the sphere, and a string, the graviton is a string state that has some size, which is of order Ls, and so gravity is a good approximation to string theory as long as Ls is smaller than the typical radius of curve of your space-time. So this is a general condition. So in this situation, you can approximate the low energy dynamics in this space-time by the gravitational dynamics, okay? That you can compute with the sort of effective actions we wrote, like the effective action of type 2b supergravity. Okay. And this requires, so this radius is what we wrote over there. So this requires that G string times n should be much bigger than 1. Okay, so now we need to find the relationship between, which I haven't discussed yet, the relationship between the Yang-Mills coupling and the string coupling. Okay? And, well, from the derivation we had here in terms of string theory, so we know that in general that the coupling of the Yang-Mills coupling here is always the open string coupling, and the open string coupling is equal to the square root of the closed string coupling. And so from that view, we see that GS is the same as G squared Yang-Mills times n. So we see that these two regimes are perfectly incompatible. So either this is much more than 1 or it is much bigger than 1, right? So the two approximations are valid in perfectly incompatible regions in parameter space, and this is good. So if this hadn't been the case, if there was an overlapping region of validity, then we would have immediately run into contradictions. Because Yang-Mills theory, weakly coupled Yang-Mills theory, is very different than a gravitational theory. Okay? So whenever you're thinking that some duality is true or not, you should check that the regimes where the theories are easy to analyze should be perfectly incompatible if you have two different looking theories. Okay? Okay. Now, of course, this fact makes this duality hard to prove, because in order to prove it, in order to even to check it, what you would need to do is you would need to do some computation, let's say in the Yang-Mills theory, and in order to compare it to gravity, you have to somehow be able to do this computation at very strong coupling. So you have to be very powerful, lots of Feynman diagrams, and do your computation at strong coupling if you really want to do a comparison. Okay. So it makes it hard to prove or hard to disprove, but it also makes it useful, because if you're interested in the field theory of strong coupling, that looks like a very complicated problem. If you do believe the duality, then it translates into an easy problem in the gravitational theory. Okay. Now, this particular theory has the nice feature that it has a lot of supersymmetry, and then there are many things that can be computed that are independent of G, okay? And so they can be computed at weak coupling in the field theory, and they don't depend on G, so they should translate to some calculation here, and you can find the corresponding calculation here and check that that they are equal, that you get the same result for those particular calculations on both sides. And in this way, you do checks of the relationship. Of course, the computation of the free energy is not such a computation. It's not a computation that is protected by supersymmetry. We got a different answer at weak and strong coupling. Okay? In fact, what you expect here, so we said here in general we expect this function of G squared n, and so as a function of G squared n, this function f, well, what should its behavior be? Well, this is 1, so at weak coupling we have 4/3, which was the field theory result, and at strong coupling we have 1, which was the gravity result, this function should somehow interpolate between these two sides. Okay. I drew it this way, but nobody really computed this function. Now people did compute the second correction to Young Mills, and they found that it curves a little bit down. And people computed the first alpha prime correction to the supergravity solution. So here, this is a gravity solution that is a solution to the lowest order equations in alpha prime, to the effective action of string theory to lowest order in alpha prime. You can consider the next correction, and people found it curves a little bit up. So anyway, so they found some variations on the two sides from the constant result, and well, it's another exercise to show find the interpolating curve. Okay, let's see. Do you have some questions? Are there any questions? Yeah. Yes. 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 They do change. So conformal symmetry is a symmetry of going to low energies to high energies, right? But not going from weak to strong coupling. When you go from weak to strong coupling, you are changing the theory. Okay. So it so happens that in some theories where the coupling runs with the energy, going to high energy is like going to weak coupling. But this is not true in particular for conformal field theory. So and here is an example of some calculation where the result is conformal. So conformal invariance, the only thing it implies is that it goes like t cubed. And it's indeed consistent with that. So when we check that these two are similar, well, the fact that it goes like t cubed should not be a surprise. The agreement between the t cubes should not be a surprise, because that's a consequence of the symmetries we already matched. We already said that the AdS has the same symmetries as a conformal Young-Mills theory. So once those symmetries matched, well, this also had to match. Yes. Yes. This what? No, low energies is independent of the coupling, because the coupling is constant, it's independent of the energies. Okay? So it's just a feature of some theories like QCD where the coupling runs, that going to high energies is going to weak coupling, but the coupling is just constant. Now, yeah. Okay. Now, something I haven't explained so far is why gravity computations really go like n squared. So, well, we observed it goes like n squared, but let me try to explain one feature of gravity computations. So it turns out that now when you think about string theory on AdS 5 crosses 5, so you have some parameters, and so one parameter is the string coupling, another parameter is n, so the number of units of flux, and one thing you can ask yourself is, well, is alpha prime another parameter? Do we have alpha prime as some other parameter? And the answer is not really. I mean, alpha prime sets some scale, but it's not really a parameter in the theory. So things will not depend on alpha prime. Now, so separately from these quantities. So a good way to think about it is to choose units where the radius, so there we see that the radius of AdS is something in terms of L string or something in terms of L Planck. And so depending on whether we choose Planck units or string units, we'll see different values for the radius of AdS. And something convenient is say that the radius, choose units where the radius of AdS is just 1, okay? And so if we choose such units, then LS, we can compute LS from that formula. And so that gives us that alpha prime is equal to 1 over square root of g squared Young Mills times n. Okay? Now, if we take this solution with radius equal to 1 and we insert it in the Einstein action, in the full type 2B supergravity action, then we'll find that the supergravity action has some n Planck to the 8 in front, and then some r square root of g and a bunch of things. And n Planck to the 8 was just equal to n squared. Okay? So when we work in these units, the action really has some overall power of n times the action, let's say, with n equal to 1. Okay? That is to say, times some action where the radius of AdS is 1, and we have all the interactions of gravity. So what this is saying is that any computation that you do in gravity will always be proportional to n squared. Okay? So we'll later see examples of computations, and here this is one example. So computing the entropy of a black hole, that's the same as computing the gravitational action of. So computing the free energy is the same as computing the gravitational action for the black brane we wrote before, and when computing the entropy, just taking some derivatives with respect to the temperature. So we'll have the same n squared dependence as this free energy. And so that's why we get this n squared. And then, so that's the leading gravitational action is of this form. So anything that we do purely in gravity will depend on n squared, but will be independent of g squared n. Okay? So an example of that is that entropy. It depended on n squared, but it didn't depend on g squared n. Now, this action has, when we're writing in flat space, some alpha prime corrections. So I think the first one is, let's say, alpha prime cubed times the curvature to the 4th, something like that. Okay? So these corrections will induce some dependence on g squared n. So the first correction to that result is some correction which will go like this alpha prime cube, or like 1 over g squared n Young Mills to the power 3/2. Okay? So that will be the first correction to this result. So this is 1 plus that power that we wrote over there. Okay? What are the corrections here in the field? What's the g squared n dependence of the first correction in the field theory? Well, like here, 1 over n corrections. Let's see. Well, 1 over n corrections, here we are not talking yet about 1 over n corrections. So we could, and in a second I will, but here we're taking the top limit, where we take the leading term in n, which goes like n squared, and then we consider corrections in g squared n, right? So the leading correction here will go g squared n, right? I mean, that's the counting we saw. Well, this is, it's very, well. Okay, so what else? Okay, so far we've seen how to compute some things. So we've seen how to compute the entropy in the gravitational side. So now let us discuss more. Oh, sorry, I promised to say something about 1 over n corrections. So then we have this parameter that this was alpha prime, and then we also have g string, and we can have corrections here as powers of g string. So the effective action in 10 dimensions, so it starts out with the leading term, but then it also has g string corrections. Okay, so the next correction to this will go like g string squared, right? So that's a correction to the effective action, and well, these are just corrections which are powers of g, or similarly we can think of them as powers of 1 over n. Okay, So if you get a power of 3 without the n, you can just multiply it and divide by n, and those are just powers of n. Okay, so let's see, any other questions? Yes, yes. Well, I think the answer to your question is that if we from larger n counting, it always should depend on n squared. And what will happen is that the value of the radius will not go like, will not have the dependence that we had here. Will have a different dependence. Yes. No, I don't think it's an independent. I mean, this fact really comes back to the fact that we had the this f square and so on. If we did the same computation in I mean, here we used that in some other places. So let me just think a second. So the same computation in 4 dimensions also gives you an n squared. Okay? Yeah. Mm-hmm. So the same computation if you did the same thing in 4 dimensions and you say that n is equal to the flux over the S2, you'd still get the n squared. It's just the fact that here you have a term of order n squared and you're balancing these 2 terms, so you'll get something of this order of magnitude. Okay. Now, okay, so now we're going to start discussing the computation of correlation functions. So, in a quantum field theory, some of the primary observables are correlation functions of operators. So we are going to be interested in the field theory. So we'll have some operators, some of this gauge invariant operator trace of some fields. So for example, phi 1, phi I2, etc. So these are the scalar fields of the Young-Mills theory, and these are indices that go from 1 to 6. So we can form these operators, and we would like to, for example, compute their correlation functions. Okay. Now, how do we do that? Well, in the field theory side, something that is useful sometimes to do is to consider the generating function of correlation functions. So that is, you introduce some function phi of x, you integrate d for x, and you take your operator O of x. Okay. And so this is this would be a function of this, let's say this phi naught. This is just an ordinary function. O is an operator in the conformal field theory, and you compute this generating function, and then correlation functions are obtained by taking derivative with respect to phi. So a second derivative with respect to phi, and then of this object, and then setting phi equal to 0 will give us the 2-point function. Okay. Now, how do we translate that computation to a computation in the gravity side? So the prescription is the following. Each single trace operator like that one corresponds to a field in the gravity theory. So a field, let's say, by x. So x is a field in 5 dimensions that depend on x and c. So these are the 4 dimensions where the field theory lives, and this is this extra 5th dimension. So we have a field in 5 dimensions, and then there is a corresponding, this is a field that corresponds to the operator. Now, finding which field corresponds to which operator is in general something complicated. And for some simple cases, the symmetries will determine the relationship. So, for example, fluctuations, if the field is fluctuations of the 5-dimensional metric, that will be related to the operator in the field theory, which is the stress tensor of the field theory, d mu nu of x. Okay? And here we can understand this because, well, the stress tensor is the response of the theory to variations in the metric, and well, here we have this metric in the interior, so it sounds that there should be, that sounds like the right relationship. Okay. We'll later see some examples of fields and operators. For the moment, let me just state that for each field, there will be a corresponding operator. Now, this field will be AdS, and on the boundary of AdS, we'll need to impose some boundary condition for the field. Okay? We discussed that yesterday, that in general, we need to supply some boundary conditions for the field phi. So we are going to say that the boundary condition for the field phi at in these coordinates where c equal to 0 is the boundary of AdS, that's equal to this function that we were given above. So that's the same function that appears over there. So this is the boundary condition for the field. And then we can compute the gravity partition function with this field obeying this boundary condition. So this will be equal to the quantity we computed over there in the field theory. Maybe so the relationship is that this is equal to the gravity partition function with the boundary condition that the field phi at c equal to 0 is equal to phi naught of x. Okay? Now, what is this gravity partition function? Well, let's before saying its full definition, let's just say what it is. This is conjecture. This is a conjecture. Okay? So the rest are definitions. So the relationship between phi and the operator is part of the conjecture, right? So because here we have phi on the right-hand side, and here we have operator. So in order to make the conjecture, we need to associate an operator to a field phi. Okay? Yes. No, we are not going to use it equal to 0 if we want to compute correlation functions. So what we're going to do is we are going to take it non-zero and then take derivatives. Yes. 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 Yeah, but the important thing is that the correlation functions will be the response to turning on a little bit phi naught. Okay? You perturb the field theory a little bit by adding a non-zero phi naught. Maybe I'll state this in. Let me approximate this by the gravity computation, and maybe it will become a little more clear. So here what we do is we approximate this by just the classical gravity action evaluated on a solution of the Laplace equation or the field equation for phi with these boundary conditions. So this is the leading approximation. So we have a gravity theory, and we have some field phi that lives in AdS with an action to leading order is just, let's say, a quadratic action like that. Let's say it's a massless field for the moment. You can do the same for a massive field. Then what you do is you solve the field equations. That is, you find a solution Laplacian equal to 0, and with the boundary conditions we stated here, and that will give you a particular solution. You plug that solution here into the gravitation function, you compute the action, and you obtain something. So the something you obtain function. It's an approximation to this correlation function in this case, because we have approximated this full partition function by this leading order contribution. Exactly, yes. Yeah, the phi that is here is the 5-dimensional phi. Here you have some phi naught at the boundary, which is this generating the function that appears in the generated function. Okay. So let me state this in a slightly different way, which hopefully will clarify it a little bit. So that's the most general statement. So let me now make slightly more concrete statement. So suppose you're interested in computing a two-point function. So some correlation function of two operators, O of x1 and O of x2. x1 and x2 are 2 points on the boundary. So this would be x1 and this would be x2. Okay? So in the field theory, you compute this by computing Feynman diagrams. The field theory Feynman diagrams in terms of exchange of gluons, etc. In the gravity theory, what you do is you take a quantum of this field phi that propagates from point x1 to point x2. Okay? So this is the leading contribution to this two-point function. Then further contributions come from more complicated Feynman diagrams here. Okay? Similarly, if you consider an n-point function, so you have disconnected contributions like this, you have connected contributions like that, and so on. Okay? And when we make this approximation of evaluating just the classical action, if we do it to all orders if we do exactly what evaluating not just the free action, but the full nonlinear corrections here, and evaluating that solution, that's equivalent to summing all the three diagrams. Okay? Yes. Okay, so this is a function of phi. In the end, this whole thing will be a function of phi naught, because this will eventually depend on the values of the boundary conditions that you have put. Okay, maybe I could do an example. What? Okay, I'm going to discuss it a little more explicitly. Okay. Yeah. So it's basically what I said. You solve the classical equations of motion for phi with given boundary conditions, and then you plug in the solution back into the action. In the language of classical mechanics, what you are doing is you are computing sort of the action as a function of the final boundary conditions. This is the Hamilton-Jacobi way of thinking about classical mechanics. But anyway, so let's see. Maybe I should try to be a little more explicit here. So before I discuss some examples, let me discuss a little more in detail how we do this computation. So suppose I have a massive field. It could be massless, but some field, right, with a quadratic action. Here we are going to approximate the full action of supergravity by just its quadratic approximation. Okay, so we're going to do something simple. Now we are interested in solving the classical equations with given boundary conditions. Okay, so this is some kind of Laplace equation: grad square minus grad square plus m square phi equal to 0, with fixed boundary conditions on the boundary. So this is the kind of problems we solved in electromagnetism, right? So we have a cavity, we solve Laplace's equation with fixed boundary conditions. And in that context, it's useful to introduce Green's functions. So a Green's function is a solution with this, that the boundary condition phi of x naught is just delta of x minus x naught, okay? So you make some perturbation at this point with a delta function, you set it 0 everywhere else, and you solve this problem, okay? And what you find is the Green's function, which will depend on a point in the bulk, where you are evaluating the Green's function, and a point on the boundary, which is this x naught that we talked about here, And this will be something of the form C. So it turns out that this Green's function has this form, C to the delta times divided by this quantity to the delta power, where delta is delta is 2 plus square root of 4 plus m r squared. So this value of delta you just get by solving the equations, and you find this simple form. So I'm just writing it explicitly, but some function. Okay. Okay, so that's what you get, and so this tells you what sort of what the Green's function is. And now, if you want to compute the 2-point function here, that's the result you get is similar to taking this Green's function and evaluating it at this point, right? That's you know, like in electromagnetism, if you have two charges and you want to compute the energy of these two charges, you can solve the equations and plug them back into the action, or you can say, well, I solved the equations for one charge and I put the other as a test charge in the first one. So here you can do the same thing, and it turns out then that the 2-point function is just the limit of this quantity when x tends to the boundary. So when this point goes to the boundary, that is when c goes to 0. So when c goes to 0, this computation goes to well, it will go. This factor here will go to 0. Let's forget for the moment about that factor. I'll probably explain it next time how we get rid of it. But so we eventually get something that goes like x minus x naught. So this was the point x naught, and this is now the point x, both on the boundary. And this 2-point function goes like x minus x naught to the 2 delta. And that is that is the linear contribution here in this action. So what we'll have for this particular example is so we have phi of x naught. So it's the quadratic contribution phi of x, and then integral d for x, d for x naught. Over x minus x naught to the power 2 delta. Okay. So this is very similar to what we do in electromagnetism. So we have some boundary conditions, we compute, and so on. Okay, so now we are ready to take derivatives and the 2-point function. So we take two derivatives, one with respect to phi at x naught and one with respect to phi at x. And so what we find is that O of x naught is equal to 1 over x minus x naught to the power 2 delta. Okay. So this here we have computed this 2-point function of this operator. So here we just have seen one example of a calculation. So from properties of this field, so here the whole answer really is this delta, what this delta is. And this delta is related to the mass of the field through this equation, and we got this equation by solving this wave equation. Okay, and delta, so now that we have this result, we see that delta has the interpretation of the conformal weight of the operator O. Okay? Because in a conformal field theory, 2-point functions of two operators with definite conformal weight have to have this form. Okay. So what we see is that this formula here is a formula that relates the conformal weight of an operator to the mass of the field in AdS5. Okay. Now, for example, if you have a massless field. So massless field corresponds to delta equal to 4. So if m is equal to 0, then delta is equal to 4. And so that delta equal to 4 in 4 dimensions, that's a marginal operator. So for example, if you take the dilaton, the 10-dimensional dilaton, and you consider the zero Kaluza-Klein mode on the sphere, then that will be a field that is massless in AdS, and that field corresponds to an operator of dimension 4, and this operator of dimension 4 is the operator that changes the coupling. So this, roughly speaking, this operator of dimension 4 is trace f squared plus, well, some other terms, okay? So this is the operator that corresponds to the zeroth Kaluza-Klein mode of the dilaton. So we have the dilaton in 10 dimensions, so it will depend on these coordinates, and we expand it in terms of Kaluza-Klein modes. So it will be a function of the coordinates on the sphere, and so we express this as a sum from L equal to 0 to infinity of phi L of x and c, y Lm, well, some other indices of theta, so the Kaluza-Klein harmonics on S5. And so each Kaluza-Klein harmonic will give us a field in 4 dimensions. And a field with mass m times r equal to L times L plus 4, I guess. Is it plus 4? Yeah. So these are the eigenvalues of the sort of L square in 4 dimensions. So by inserting, so this is the squared. So inserting this into this formula, you see that each Kaluza-Klein mode will have dimension delta equal to, well, you can check this as you plug this formula in there, you get this result. Okay. So what we just checked was the case L equal to 0. So this is the operator that corresponds to the field phi L equal to 0, the 0 mode of the 0 Kaluza-Klein harmonic on the sphere for the dilaton. And then, roughly speaking, as you start increasing L, so phi, let's say with L equal to 1, that's something that has 1 index on the sphere. So it's roughly speaking this operator, phi I. Okay. So you add one of the scalar fields that has some SO6 index. And then if you want to go to L equal to 2, so you say O trace f square phi I1 phi I2. Now you have these two SO6 indices, and in order for it to have the properties of the L equal to 2 spherical harmonic, what you need is to take the traceless part. Okay. So the trace is a singlet under, but that's not part of how Kaluza-Klein harmonic works. So this is phi L equal to 2. Phi equal to L equal to 3, and so on, so you can figure out. And something you see is that this operator has dimension 4, so that's the change in the coupling. That's what's to be expected. And that we said it was a marginal deformation, so the theory is conformal for all values of the coupling, so definitely this field has to have dimension 4. Now, the dimension of this field at weak coupling, so if we compute it at weak coupling, the dimension is just the sum of the dimensions of each field. So we have f squared has dimension 4, and we added 1 phi. Phi has dimension 1. So that we have this 4 plus, and if we add L phi's, we'll have 4 plus L. Okay. Now this was the dimension. This dimension here was the dimension computed at strong coupling, and we see is equal to the dimension computed at weak coupling. Okay. So both are the same. Now this didn't have to be the case, but it is the case here because these operators are in some special multiplets of supersymmetry. So they are in they are in some multiplets of supersymmetry which do not receive, which are a bit shorter than the generic multiplet. So the generic multiplet of operators, you start with some operator O, you act with Q, you get another operator, and so on, and you get a bunch of operators until you act with Q to the 16 O. Then if you add more times, you start getting descendants, etc. So this is the big long multiplet, and this can have any dimension. As you change the coupling, the dimension can change. But if the multiplet for some reason is shorter, and this can happen if the dimension of this or operator is related to L in some way, I'm not going to be very explicit. So if this multiplet is shorter, then the dimension will be linked to the SO6 quantum numbers of the operators. And those operators therefore have a dimension which is given in terms of their SO6 quantum numbers and is independent of the coupling. So the fact that we got this a corresponding field here is a check of the correspondence. And this is one of the checks that can be easily done. And here we could do it due to supersymmetry, due to this shortening of the multiplets. And in fact, all the Kaluza-Klein harmonics of supergravity on AdS5, they are all in some protected multiplets. And the Yang-Mills theory does not have other protected multiplets. If it did, then it would be a contradiction to AdS-CFT, and AdS-CFT would be wrong. Okay. Now, I've been talking about all these fields that don't have any correction, so you should not get the impression that all operators do not have any corrections. Actually, most operators do have some corrections. So, for example, if you consider the operator trace phi squared, so phi I, this is a singlet of SO6, at weak coupling, so when chi squared n is much more than 1, this has dimension equal to 2. But in AdS, we have already exhausted all the Kaluza-Klein harmonics, matching them to all these kinds of operators. And there's actually nothing left over to match it to this operator among the supergravity fields. Okay? So what could happen with this operator? Well, what will happen is that this operator will get a dimension, will get a mass in AdS. Well, first of all, it cannot be a supergravity field for the reasons I have just explained. And so the lightest it can be is a massive string mode. So massive string mode will have tension, will have mass 1 over Ls. This is a mass which is much bigger than 1 over R in the supergravity region, where R is very large in the string unit. So if then delta will be of order mr, and through the formula that is over there in the blackboard, so we find that this goes like chi squared n to the 1/4. So this operator at strong tough coupling gets a large dimension, which is proportional to the tough coupling to the power 1/4. Okay. Now, as I was trying to emphasize, most operators get large dimensions. In particular, in Yang-Mills theory, you have lots of operators with higher spin. So, for example, you can construct. So here we had one simple operator, but you can take operators where you take derivatives to the nth power of this operator, and here you can combine the indices of the derivatives in such a way that you have very high spin. Okay. Now, in supergravity, we only have spins less or equal than 2. Okay. So, in order for supergravity to be valid, then you should find that the conformal dimension of all the spins bigger than 2 should always be bigger. So it should be bigger or equal than this Gn to the 1/4. Okay, so they all should get some large conformal dimensions. Now, the result is really a very general result. So if you have any field theory that is supposedly dual to some gravity theory as opposed to string theory, that is to say, is dual to a gravitational background that is has a radius larger than the string scale, then the corresponding field theory should have all operators with spin bigger than 2 should be large. Okay, so large in the same proportion that the radius of curvature of the space is bigger than the string scale. Okay. Okay, so if you have some questions, I'll finish here.